All right, so my name is Richard Steenbergen from GTT, and I'm doing a tutorial on an introduction to MPLS. So the purpose of this tutorial, well, we're not here to talk about the usual details, protocol specifications, packet headers, label operations, any of the fancy technical stuff. The real goal of this talk is to introduce the basic concepts of MPLS to people who have never used it before, explain how MPLS can help you improve your network, really kind of enumerate through all the features, all the different uses for MPLS and where you can see advantages, and also to kind of help overcome a lot of the fears associated with it. There's still a good historical community of people who are IP-centric, who are kind of afraid of MPLS. It looks like ATM, kind of smells like ATM. It does some weird, complicated stuff. It has a reputation for being complex. In a lot of ways, that's true, but there's also a lot of benefits to it, and it's the kind of thing that everyone should look at if you run any kind of network of size. So here's the target audience. Actually, the screen resolution on this might not be perfect. Yes, our friend Dave Bannister with his MPLS sucks license plates. So, the basics. MPLS stands for multi-protocol label switching. So the best way to think about MPLS is as a layer 2.5 protocol. It fits right in between where the traditional internet at layer 3 goes and a layer 2 network, which is typically a small network or a point-to-point WAN circuit, but it really doesn't let you do anything complicated on a large national global scale in terms of delivering layer 2 services. So there's no layer for it in the OSI model, therefore we call it a layer 2.5 protocol. So what is it? If you think about the way a traditional IP network works, each router is doing a routing lookup. So each router is making its own independent determination. It does a lookup, comes up with a next hop, forwards it to the next router, and then the next router does the exact same thing. And what you're hoping is that all of your routers are in sync, they've all decided the correct thing, and are all pointing the packet the same way, and eventually it gets there. What MPLS does is label switching. So what happens here is the first device, when you take it in, does the lookup in the routing table just like normal. But instead of finding a next hop, it finds the actual final destination router. And then it tunnels that packet inside of a path. It's called an LSP, a label switched path. So it applies a label to that packet. And then when it forwards it, all the future routers, instead of having to do that original routing lookup and come to the same conclusion and forward it in the same direction, they're no longer routing based on IP. They're now switching based on the MPLS label that was added. So it lets you predetermine the route through the network at the very beginning. And then when it gets to the end, the label's removed, it becomes a normal IP packet again, and it forwards. So what are the advantages? Originally, if you look back at the history of MPLS, it was intended to reduce IP routing lookups. So an interesting thing about the history of the internet and when CIDR was created, it actually had a bunch of unintended consequences. So the original premise of CIDR was if we let people allocate and suballocate smaller blocks, it'll make IP usage more efficient, and that's true. But it also makes routing lookups much harder. Instead of an exact match look, you're now, in a lot of cases, walking a tree. So the original structure to do this was called a Patricia tree. It's just a radix tree. And so if you've got someone with a /8 who then allocates it to a /9, who then reallocates it to a /10 all the way down, you might be doing 20 lookups, 20 memory accesses, 20 pointer walks, and it was really slow. So in a lot of ways, the deployment of CIDR actually slowed down the growth of the internet in the early stages. And MPLS was a workaround for this because exact matches are much easier to implement, especially in hardware and especially at the time. If you looked at a lot of early routers in the way that they did the performance, they cheated a little bit in software. They did the first lookup in software too, and then they would program the results in hardware. And that worked as long as the traffic was normal, and it tended to break down really quickly when you had, for example, a worm that would start scanning a lot of destinations and would overload the hardware. So MPLS was the solution for this. You do your routing lookup on the edge, you label it once, and now you've taken that routing lookup load away from all of those other routers that you come along. And the original idea of reduce load on the core routers, push it out to the edge, distribute the routing lookups, and this would help the network scale. It turns out this isn't really a problem anymore. So what happened is modern ASICs came along and we figured out how to do hundreds of millions of packets per second of lookups in very cheap commodity ASICs. So it's really not necessary anymore, but in some ways it is still a significant portion of the cost of the router. So if you look at what makes your big expensive router big and expensive, a lot of it is the size of the FIB that has to be installed. And since the routing table is always growing, that gets more and more complicated. So there would be an advantage in building an MPLS only core box. It's a much simpler box. It looks much more like a layer 2 switch. And if you've seen pricing on cheap small layer 2 switches, an MPLS box could be in that ballpark. But so now that we don't really need MPLS to solve the performance issues anymore, the question is, why do people still care? And it really breaks down to three main reasons. The first is to implement traffic engineering. So that's the ability to control how the traffic is routed on your network in a much more granular way than just looking at IGP costs and hoping that the routing works out and hoping that you have enough capacity. It lets you do things more constructively with the capacity that you have. And so it's ultimately a money savings tool for a lot of networks. The next one is to implement multi-service. So we're no longer talking about just IP on your IP network. We're now talking about transport services. We're now talking about being able to go out and sell every different form of service to every different enterprise and other carrier and provide virtual circuits to other people. So it opens up a whole new world of additional services besides IP. And then the third main reason is to improve network resiliency. So MPLS gives you a lot of performance enhancements when you've got failures, flapping links, failing routers. It lets you react to those in a much smarter way and have better performance. So dig into a little bit of the details of how MPLS actually works. So like I said, MPLS uses what's called a label switched path, an LSP. And the concept here is this is a one-way tunnel, essentially. So you have the start of the ingress is called the label edge router, or the ingress node. That's the router that's responsible for figuring out where it wants the packet to go, encapsulating it inside the LSP, and forwarding it on. The devices in the middle are called LSRs, label switching routers, or transit nodes. And that's a router that's only doing MPLS switching. So it never needed to do an IP lookup in the first place. All it's doing is looking at a label and forwarding it to the correct interface. And then when you get to the egress node, that's the final router of the LSP, which removes the label. And I'll get into some more details about other ways that the labels can get removed later. But that's the basic concept. Think of it as a one-way tunnel from point A to point B. And how it gets across your network is what MPLS is there to help you determine. The other way that you see these roles expressed a lot is in terms of the way people talk about it as VPN services. So a P device is a provider device. It's that core box that isn't talking to anything edge, isn't doing anything other than MPLS switching. And the PE, the provider edge, which is the ingress and egress node. And then, when you get around to talking to the customer devices, when you're looking at network maps, you'll see it labeled as CE. But those are the real roles. And the PE is the one that does a lot of the work, figuring out whether it's internet, whether it's L3 VPNs, L2 VPNs, Pseudowires, VPLS. Really, the P devices in the middle could be as dumb as bricks. All they have to do is look at a 4-byte shim and forward a packet based on an exact match. So in order to make this all happen, there's a bunch of signaling protocols. So we'll talk about protocols a little bit. So remember, an LSP is a network-wide tunnel, but a label is a link local value. It only tells you how to get to the next router and what you do with it. So you need a signaling protocol to coordinate this across your network. There's two main signaling protocols that people use. The first one, the simplest one, is LDP, the Label Distribution Protocol. It's very simple, it's very straightforward, and it will distribute your labels. But the one thing it doesn't do is help you do a lot of complex traffic engineering. So ultimately, you are the one responsible for figuring out the path. If you decide that you want to move 5 gigs of traffic from Ashburn to San Jose, you pick the path, and you explain it, and then LDP will signal it and make sure that that gets carried out. The other one is RSVP-TE, or just RSVP for short. So the original RSVP protocol did something slightly different, and then they took it and adapted it into MPLS. And the main difference between that and LDP is it has a bunch of constructs for doing traffic engineering, basically for doing reservations. So what happens is it will let you say, I'm taking 5 gigs of link on this, 5 gigs of capacity on this 10 gig link. You only have 5 gigs left. And then the next device that's looking for capacity knows that. And if it needs to put 6 gigs on it, it can look somewhere else. So really what you see in usage is LDP is typically used by the very simple MPLS VPN transport services. But most networks that are doing interesting things with MPLS want to use RSVP. And the way that a lot of it ends up working is you'll tunnel your LDP signal to LSPs inside of your RSVP signal LSPs. So again, MPLS labels can be stacked multiple times. And so when you get to, here's an example of an LDP LSP. So this is a customer VPN service. And we're tunneling it through a core network that is doing RSVP, that is actually using it to do traffic engineering and find available capacity. And so you can put 2 labels on there. And when it gets to the end of one, it will pop it and then work on the next one. I'll get into some more detail on this later, but another common application for this is bypass LSPs. You can pre-compute what happens in the event of a failure, and so you might have an additional LSP for that. So you can have LSP stacks that end up being very deep. And then one other little bit of detail to talk about. It's not always popped. In fact, it's not often popped at the very last router. The 2 ways to terminate an LSP, implicit null is the default. So what happens is it's popped at the next to the last, the penultimate hop, so that the very last router gets a native IP packet and does the regular forwarding. And the reason for that is if you did an explicit null, if you made it stay in MPLS all the way to the end, then in most architectures, the final device would have to run the packet through its lookup engine twice, and so you're doing it as an optimization. But really, you can do it either way, and it's effectively the same thing. You're using MPLS to get to that final router, and it's what's making the decisions. So a little vendor terminology warning. So Cisco and Juniper are the 2 that I use here, and these are really the 2 that kind of own the MPLS market. And if you look at the protocol, they're also the ones that wrote MPLS. So there's no surprise there. There's a lot of other people that do it, but they don't do the full suite of features and products. They do some very specific things. So I really talk about Cisco and Juniper as the 2 main things to look at for MPLS. And you see these guys have different names for the same thing. So what Cisco calls affinities, Juniper calls admin groups, and auto route analysis, TE shortcuts, all of these things have different names. So there's a little table for if you're working in a multi-vendor environment or you're hearing it described one way and you want to know what it is, you can kind of consult this and do the translation between vendors. So now we talk about the first role, what I think is the most important role of MPLS, traffic engineering. So really, what is traffic engineering? So if you look at the way a classic IP network works, you have an IGP, you have a metric, a cost per link, and typically people set their metric to be something like the latency. So if it's a 50 millisecond link, it might have a metric of 500. And so you're looking for the shortest path across your network. Sorry, my laptop is doing something screwy. Okay, well, that'll work. So yeah, the classic IGP, you're finding the shortest path, but you're finding one shortest path. And typically what happens in a big complex network is there's many, many ways to get to a destination. And sometimes the shortest path is not the best path because the shortest path might be full. So traffic engineering lets you manage that. It lets you do additional constraints. So you might say, find me the shortest path that also has available bandwidth. And that's called, in the MPLS world, CSPF, Constrained Shortest Path First Algorithm. And the principle in that's very simple. It's much better to deliver the packets a little bit slower than it is to not deliver the packets. So we're looking for the best path with available bandwidth. Basically, just a way to manage complexity in a very large network. And you say, why can't I do this with my IGP costs? Well, you can to a certain point, but as you build a bigger and more complex network, it gets really difficult to manage the implications. So you might have two links and you might need to move more traffic onto one and less traffic on the other. You change your IGP cost by one, that now ripples through the network. That now changes 5, 10 hops away what stuff wants to be preferred where. And it very quickly gets unmanageable. So that's why you see all the large networks pretty much are forced to use MPLS to manage complex situations that you just can't do with basic IP. So here's an example of very simplistic network. How would you route from Chicago to Los Angeles? Very simple network. Or Los Angeles to Chicago. So here might be the very shortest path. You have one circuit to Salt Lake City and you have another Chicago, and that might be a certain latency. But you could also go this way, and this might only be 2 milliseconds higher. And so that might be a very perfectly acceptable route. That might only be 3 milliseconds higher. Again, a perfectly acceptable route and something that you would rather use in the face of congestion. Or even something like this, bypassing this Los Angeles to Dallas link and coming up this way. So again, you're looking for ways to manage the complexity and take advantage of all of the bandwidth that you have. So ultimately, MPLS is really about a cost savings tool and a way to run your network more efficiently. So how does traffic engineering actually work? So RSVP, like I said before, reserves bandwidth across the network. So remember, an LSP is essentially a tunnel between 2 points in the network. So you're saying, from this router to that router, use this LSP. And so with RSVP, what you do is you give each one of those LSPs a bandwidth value. You say, between this router in Los Angeles and this router in Chicago, I believe that this LSP is using 5 gigs. And then RSVP goes out and looks for those 5 gigs. It explores all the available paths, it looks at all the available bandwidth tools, and it says, this link has the 5 gigs that I'm looking for. And then it takes that 5 gigs off of the available bandwidth. So the next LSP comes along, looks for it, and it knows this link is already full, I need to move on to my next best path. And that's all done with the CSPF algorithm. And eventually, existing LSPs can be preempted. So you can have higher priority LSPs. You could have a customer who pays you a lot of money for a guarantee of the lowest latency route. And so you might make the lower latency routes available to other customers when there's capacity available, but you might also set it with a higher priority. So what'll happen is the lower priority customer will get kicked off, will get moved to the 3 millisecond higher link, and the person who's paying you for the guarantee of low latency will be guaranteed that path. So it's not QoS in the traditional sense. You're not dropping packets. You're just applying priority to the routing inside of the network. So here's a slide showing kind of how RSVP does it, and there's a little more technical detail than I was going to get into in here, but I had it left over in the slide deck. So you can see it passes the messages out, requests bandwidth, moves forward, and eventually finds a path with all of the available bandwidth that it needs. So then the next question becomes, how do you determine the LSP bandwidth? Because after all, IP networks are very dynamic and packet switched. So the bandwidth, what you think might be 5 gigs, can change in an instant. A session can flap, someone can launch a DDoS, someone can fire up a streaming event. 2 seconds from now, that could be 10 gigs, that could be 0 gigs. So there's 2 main ways that people go about doing this when they're doing these LSP bandwidth calculations. The first is the offline calculation method. So this is common among big carriers. What happens is you do the calculation outside of the router. You have some fancy software, some tool. You might pay a third party for it, or you might build it in-house, but you do modeling. You say, my network is large enough and stable enough that I believe the traffic will always look like this, and so my model says that tomorrow the curve is going to go like this, and I know what the peak of that curve is, and so I'm going to build my routing around that. And that was how it was first implemented, and again, there's still a lot of very large carriers who do it that way. The second method is something called auto bandwidth. And what happens here is you let the router do a measurement. So the router has counters and it knows how many packets are flowing through the LSP. And so it says, well, the last 5 minutes I've been doing this, so I need to adjust my reservation accordingly. And this is more interesting, but it tends to be a lot faster and a lot more flexible, or a lot more real time than what you can do by doing offline modeling, because the complexities of changing every configuration on every router every 5 minutes are pretty high, but if you let the router run it itself, it can be a lot more efficient. So here's an example showing kind of some of the differences between the way you do your adjustments, how often you look at it. So in a traditional offline model, the way a lot of people look at it is they kind of model it over the course of a day. Most bandwidth curves tend to be cyclical and repeat over a day cycle. So they say, this is the bandwidth that I'm going to need for the day. And the problem there is you have a lot of overlapping links with overlapping time zones, with overlapping traffic profiles, and it tends to get difficult in the event of a failure, in the event of any type of a routing change, because now you're dealing with an unknown profile. So again, if you get to a shorter adjust interval, if you can make the router more dynamic, you can react faster. So here's kind of showing the different bandwidths that you might get at a 1.5 hour adjust interval. And you can see that at the low peak, you're more aware that you have available bandwidth that you could use, and so that means less over provisioning that you have to do inside your network. So there's some advantages to each. The nice thing about offline calculation is you can implement any algorithm you want. Some people can get as complex as you want to get, and I've seen very fancy mathematical models by PhDs who do a lot of very complex software. There's a lot of third-party vendors out there who will sell you a lot of stuff, and it lets you do very detailed planning. So you can very easily go to a vendor, buy a nice software package, and you can do a model that says, what happens to my network if these 7 links fail? And you look at your traffic and you can see exactly where it would go, and let you help to do a little bit of that planning. The disadvantage is you either have to write that software yourself, which is pretty complex, or you have to buy it, pay a lot of money for it. Auto bandwidth is built into the routers on most large routers that matter. It runs directly on the router itself, so again, it can respond to changing traffic conditions much faster. It has less overhead doing it, so you're not managing the complexity of updating your config files every 5 minutes or something like that. Again, most offline calculations are based on the prediction of stable traffic patterns, so auto bandwidth really helps when you have unstable conditions. It lets you be far more efficient. And of course, it's easier to implement because just turn on the knob on your router, it's free, but you have less control. You're dependent on your vendor to get the calculation right, to do the updates right, and there's a lot of caveats that come with that. So each side has its advantages and disadvantages. And ultimately, you give up some degree of control, because at least with offline calculation, it might be less real time, but it's you are in complete control of where you route the LSP. So the next major use of MPLS is multi-service, like I was talking about, and it typically tends to be the data transport services that people are interested in. So the most common thing that you'll see in an MPLS network is what's called a layer 2 pseudowire. And it turns out there's a lot of names for these because there's a lot of competing bodies that are all trying to standardize these things. But a lot of times you'll hear it simply called a VLL, a pseudowire. There's a PWE3 IETF working group that's standardizing this. There's Metro Ethernet forums. There's all of these different competing organizations that all have their own way to describe the particular service. But basically all you're doing is you're emulating a layer 2 point-to-point circuit and you're delivering it over MPLS. So basically, if you were to sell a customer transport from Los Angeles to Chicago, it would be like giving them one really big, long Ethernet circuit. They put the frame in on one side, it comes out on the other side. And it's useful for migrating legacy transport, so you can map your ATM directly onto it. One of the weird things is that it can be difficult to load balance. So a lot of times you don't have visibility into the underlying packet that the customer is using, so you don't have as much hashing. And then if you look at the way that these are signaled, there's 2 different ways that you can go about signaling a layer 2 pseudowire. So the first method, probably the more common method, is the LDP signaled. It was called Draft Martini originally. It was the simpler, more commonly implemented method. And then there's also a BGP signaled Draft Compella L2 VPN. And there's some advantages to each, but the BGP one, you're overloading BGP. You're putting more and more stuff into BGP. But if you already have an existing BGP network with route reflectors in place, It can just work. You don't need any additional LDP signaling. It has some auto discovery support. It has some multi-point support. So more complexity, but that's an option. And some routers have gotten religious about which ones they support and which ones they don't support. And then eventually, I think at this point, almost everyone has kind of converged around being able to offer all of them. But there's some that one router vendor will prefer over the other, or that they've built their network around, or the service around being able to deliver better. The next major one is L3 VPNs. So basically think of this as an IP-based VPN. Instead of the customer passing you a packet, a layer 2 packet, a frame, and you transporting it just like a big Ethernet network, you're doing it by routing. So essentially what you're doing is you're building a virtual routing table inside of your router, a VRF, the virtual routing domain. So the customers, instead of being responsible for running their own network, they just announce a route to you. So they set up BGP, they talk to your router, but rather than using BGP to carry internet routes, you use BGP to carry the specific internal VPNs routes. So typically where you see this is enterprise environments. Anyone that isn't well-versed in running a large layer 2 network, they wouldn't know what to do with hundreds of point-to-points or even a multi-point network and running their own routing protocol or anything like that. All they want to do is they've got a branch site, and it might be 10 dot space with a /24, and all they want to do is configure a BGP session, announce that one route, and make you responsible for the rest. And this has some different scaling properties. Probably one of the biggest downsides is now the provider router is responsible for carrying these routes in their router. So it starts to add load, but it's also very load balancing friendly. You have direct access to the IP headers, you know kind of what's coming in, and you can hash more effectively on that. And again, it's very common in the enterprise environment, so there's often a lot of money attached to these services. So it's just one more way to do a point-to-point circuit. And then the latest methodology out there is VPLS, the Virtual Private LAN Service. And so basically what this is doing is it's creating an Ethernet multi-point switching service over MPLS. So basically think of it as emulating one really big giant layer 2 switch. It might span the entire world, it might have hundreds of sites, but it's effectively a layer 2 switch. So it does unknown unicast flooding. It gets a layer 2 packet in, and it says, I don't know what to do with this. I'm going to flood it to every site. I'm going to wait for a response back, and then now I'm going to know where to send it. It does MAC learning, it does broadcast, everything that you would expect from a traditional layer 2 network, that's what it does. So there's big advantages in that. If you've got a 50-site network and you wanted to create a full mesh, that might take a really long time. Or be really complicated to set up, and so it simplifies things. It also comes with all the downsides of running a big layer 2 network, broadcast storms, overhead, things that you can do. So there's, again, advantages and disadvantages to every way. And then the third major advantage of running MPLS is the ability to kind of protect around. So fast reroute is one type of that, but the ability to handle failures in a better way. So what does fast reroute do? Basically, it improves the way that you handle convergence during a failure. It lets you pre-calculate the backup path and actually pre-install it all the way down to the fib. So if you look at what happens in a normal network, say you lose a link or you lose a router, and you need to do a best path calculation on the affected link or the affected router. And it says, oh crap, we've lost this link. And right now, decide what's our next best path, and then propagate that message to the next router, which has to do its own calculation and propagate. And so if you end up with a large network and you get far away, all of a sudden you find that there's a significant lag time for all of the routers to get synchronized. It could be on the order of several seconds, even in a well-run network. So what fast reroute does is it lets you bypass all of that. It lets you, if you get desynced in an IP network, you can get transient routing loops. You can get router A thinking it's still sending to router B, and router B thinking it needs to send it back to router A, and that can persist for seconds and tends to piss off customers. So fast reroute, you pre-calculate the next best path, and you actually pre-program it into the fib. So you can literally distribute this down to the individual router line cards. So the instant they detect a failure, they know what the next path is. They can install it, and because it's an LSP, you've predetermined the path for the entire network. So you're avoiding that forwarding loop. Even if the next router that you forward to, if it were to do an IP lookup and it were to think it was to send it back, it doesn't matter because it's not doing an IP lookup. It's doing an LSP switch. So it really helps you bypass that whole transient routing loop issue. So there's a couple different ways that the MPLS protection schemes get implemented. So the first way is what's called one-to-one protection, or a detour LSP. So what happens there is there's an individual backup path that's fully signaled for every LSP. That it's essentially a bypass LSP. And so you have a label depth staying at 1. It's just an ordinary LSP, but you now signal a big pile of LSPs. You've doubled the number of LSPs that you need to signal in your network. The other way to do it is what's called a many-to-one, or a facility backup. And in that case, you have a single bypass LSP that's acting as it's stacking. So you might take 100 regular LSPs and say, I have determined that in order to provide a backup for these 100 LSPs, I have this one bypass LSP that will protect all 100 of them. And so in that case, you have multiple LSPs using that bypass LSP, and then eventually the network will detect this, re-optimize in a better fashion, and get back to not using the bypass LSPs. And then the two types of failures you're protecting against, the first one's called link protection. So that's creating a bypass LSP for every possible link failure. And the other one's called node protection, and that's looking for possible router failures. So here's a scenario. Here's a network with 5 routers, and you're forwarding linearly through 1 through 5. An MPLS network with no protection, this is your path for this LSP. So when you want to do link protection, R1 says, what happens if this link to R2 goes down? I'm going to go ahead and signal this other link, even though it might not bypass the router. And then node protection is saying, R1 is saying, what happens if R2 dies completely? What if I need to bypass it? I need to find my way to a different router. Well, I'm going to pre-calculate a way to R3, and R2 does the same thing to bypass R3. And then when you combine them, you end up with this full protection for the most common failures, your link and your node. So you have all of these different bypass LSPs signaled. So now I want to talk a little bit more detail about MPLS auto bandwidth and how that works. So the way auto bandwidth works, which is a very common way that a lot of people want to, especially if you're starting from fresh, and you want to kind of build a very efficient network that reacts quickly, you want to kind of use the tools that have been given to you by your router vendors. So auto bandwidth, technically the algorithm is completely router vendor independent. It just so happens that Cisco and Juniper implement it pretty much the same way, mostly because it was the same people that wrote it. But it follows the basic steps. These are the operations that you look at when you're doing auto bandwidth. So you start with a statistics interval. It might be, for example, 60 seconds. And you say, every 60 seconds, I'm going to do a diff in the number of packets that were there before to the number of packets that are there now, and so I know my average rate over the last 60 seconds. And then you have what's called an adjust interval. So you say, I want to take multiple of these statistics intervals and figure out, do I need to make an adjustment in my reservation? And how often should that be? So for example, you might do a 5-minute adjust interval, looking at 5 of those 60-second samples. And you say, well, the adjust interval's up, it's been 300 seconds. Now I'm looking at it and I say, is the value that wants to go across worth changing? Is it more than, and you could configure, you could say, for example, I only want to change if it's more than 5%. So if there's been a 5% change in the reservation, you say, okay, it's time to resignal, and you go out and create a new LSP with a new bandwidth, and you tear down the old one. And there's a way to do this gracefully called make before break. So what happens is it goes out, reserves that, builds the LSP, creates it, puts traffic on it, and then takes down the old one. Otherwise, you have an impact every time you re-optimize, which is bad. So here's an example of what happens when auto bandwidth works really well. So you see, you look at your previous statistics here on the left, and you say, well, this was my peak, and this is how much I think the bandwidth needs to be. And then your next cycle, you go make that reservation, and it tends to be pretty correct. And then the next cycle, again, you say, hey, it lowered by a little bit, so I'm going to go lower my bandwidth reservation, and then again, you turned out to be pretty correct. Where it doesn't work well is when you have highly variable traffic patterns over very large intervals. So say, for example, in this first one, you have a peak to 50-something megs, gigs, terabits, whatever. And you say, oh, well, this link is really full. I really need to raise my reservation. So the next adjust interval comes along, you make your adjustment, and then turns out you were wrong. The bandwidth dropped a lot. And so you go, oh, never mind, I was wrong. Lower that adjust interval, lower that bandwidth, and then turns out you were wrong again because the bandwidth is on its way back up. So this is what happens when you set your adjust interval long enough that you're looking at significant changes to the traffic pattern. That's why a lot of people standardize around daily, because daily was a typical full cycle in traffic pattern. So this is the kind of situation you want to avoid. So there's some ways to work around this. The ways that the routers implement are called overflow and underflow. So the logic says, normally my adjust interval, and so there's a lot of people that want to run their adjust intervals at 4 hours, for example. But you say, well, normally I would only adjust in 4 hours because I'm looking to optimize my network. I want to go resignal every LSP every 5 minutes if I don't need to. But in the event that I see a certain number of statistic samples exceed a certain difference, I'm going to kick off an adjust interval early. So you might say, in the previous scenario here, whoops, I really wasn't expecting that sample at 50, and if I see 2 or 3 of those in a row, I might decide that it's time to make my adjustment now instead of waiting. And that's overflow. An underflow is the same logic in reverse. It's the ability to detect that it's significantly decreased and that you might need to go out and recover bandwidth. Underflow is actually relatively new, so there's a lot of vendors that still don't support it or support it well or fully. I think Juniper finally just added it. It's in XR. I don't think it's actually in regular iOS, or it wasn't the last time I looked. But the advantage of overflow is that it catches significant increases in traffic that might cause loss. The advantage in underflow is that it helps you recover wasted bandwidth. So if you're still out there reserving for a 5 gig LSP and it's turned to 1, you might want to know that, because that's 4 gigs you can get back and do something else with. So if you don't have these things, it can lead to suboptimal routing, or even a situation where the LSPs can't signal at all, and that's bad. So a little more details. I talked earlier about LSP priorities. So the LSPs actually have the ability to preempt each other. So an example I gave before was you might have a high priority customer who pays you a premium to guarantee a low latency route. Another example might be you have traffic that you've determined is highly likely to be denial of service. This might be large packet NTP, for example, or it might be coming from certain networks in China, for example. And you decide this is probably traffic that I want to drop first or route slower first. You can set up different priorities. And there's 2 priorities that come into play here. The first one is the setup priority. That's what determines how the tunnel gets established. And the next one is the hold priority. It's the priority of how much you are willing to stay on the current path versus whether you're willing to be preempted. And there's 2 types of preemptions. There's a hard preemption. So in that case, the LSP is torn down in a disruptive manner, which is generally bad. And then there's a feature that you want to use called soft preemption. And that gives the LSP time. It gives it tens of seconds to go find another path, tear itself down, and let the higher priority LSP come in and take over the bandwidth that it's looking for. And that tends to be mostly non-disruptive. So here's an example that I'm not entirely sure is translatable on here. It's just the basic concepts that I was showing. I'll kind of skip these slides. Showing you've got a higher priority LSP coming in, it's kicking the lower priority LSP off, and then it goes and finds the next best path for itself. So another feature that you care about is LSP optimization. So over time, the network topologies change. The IGP costs change, you add new links, you have failed links. you want to re-optimize the deployment of your LSPs. So there's an optimization process that comes along periodically and looks at it and says, is everything going where I want it to go, and is everything being efficient about it? And if there's new, better paths, it will go try to rebuild and move the LSP. Some cases you may not care. For example, if there was a link failure on your primary route and you moved it to your secondary, which is 1 millisecond higher, it might not be the end of the world to leave it on that 1 millisecond higher link, especially if it just flapped. You might want to wait 5, 10, 15, 30 minutes to guarantee that it's stable before you move it back. And so most routers have a feature, it's called a smart optimization. So for example, you can have an optimization that occurs when a link comes back up. You say, oh, I've restored capacity and it's been stable for this much time. I want to re-optimize into it. But if I see it flapping a lot, I'm not going to re-optimize onto it. I'm going to wait until it's stable. So make before break, I talked about it earlier, but that's when the LSP is re-signaled for any reason. The old LSP is torn down and a new one's built in its place. And if you do it by default, if you don't turn on your make before break or your adaptive LSPs, this is a disruptive process. So it turns out even updating a bandwidth reservation requires a new LSP. You can't just say, hey, I have this LSP, it's in place, everything's happy hunky-dory, but I just want to change it from 5 gigs to 6 gigs. You actually have to build a new 6 gig LSP and then tear down your old 5 gig LSP. So when you use the make before break or adaptive LSP feature, it does that. It goes out, builds a new one, tears down the old one, and avoids that traffic disruption. And it does this by a little trick. It lets you do a little bit of transient double counting of bandwidth. So when there's a new and an old LSP sharing the same path, it knows that this is going away in just a few seconds. But if the paths are very different, they might actually be reserved twice for a few seconds. And so usually this is a very transient thing, and it goes away quickly. So then the next question becomes, I've got all these LSPs in my network. How do I use them to route my IP traffic, my internet traffic? And there's a couple different ways you can do this. There's some networks that choose to do it entirely by static routes. You can literally say, I want to take this route or this specific thing and forward it into this LSP. It's a handy way to do some quick, dirty traffic engineering, but it's not very scalable. So really what you want is protocol extensions that let you take your normal IGP or your normal BGP, and instead of doing only a routing lookup, it now says I can use my LSPs as a resolution for my next hop. So let's the local router use the LSPs. Cisco does this transparently by modifying the SPF algorithm. The way Juniper does it is it has a routing table called inet.3. Where it installs the LSP stuff. And when you enable these shortcuts, essentially all you're doing is you're letting the route use an LSP to reach its destination. So even if the original destination doesn't speak MPLS, the LSP will take you all the way to that last destination that does. There's a few things about MPLS and Traceroute that everyone needs to be aware of. One of the features that MPLS is known or renowned or maybe not liked for is the ability to hide traceroute hops. So remember, you're not actually doing IP forwarding. When you're moving a packet through an LSP, you're just doing label switching. So there's no need technically to decrement the IP TTL field. And so you could have your entire LSP show up as one router hop instead of however many that it needs to go through. There's a lot of networks that actually prefer this. There's people that have religious beliefs that number of hops equals bad, and so if they see a network that only has a few hops, they think their packet got there faster somehow, even though it went through the exact same everything. And so there's people that do this intentionally to market to those customers. There's people that do this intentionally because there's a lot of customers who are running Windows boxes with traceroute TTL set low, and so if you have a big complex network with a lot of routers, you might not even be able to have your ordinary end customer get all the way across your network. Some people do it for secrecy. Some people just choose to turn that feature off. And it's actually more work. You actually technically have to turn a feature on to enable TTL decrement inside of an LSP, because that's not normally part of the operation. But one of the more interesting things out there is there's some networks who run an MPLS-only core. So like I was talking about earlier, it's possible to build a more efficient network or router that doesn't need to carry a routing table. It's only doing, if you have a core box that does nothing but label switching, you can build an MPLS-only box, not carry a routing table. It might be cheaper to implement. Some people do it just to do it. But there's a little bit of a downside to that, because now when you're generating your ICMP-TE LSP, if you don't have a routing table on your core box, you don't know where to send the TTL exceed. That's the normal operation of Traceroute, is when that router drops the packet, generates the stuff, it does a routing lookup and sends it back out the correct destination. So the workaround for this is something called ICMP tunneling. And what happens is, say that router in the middle drops a packet because it's hit a TTL exceed. Rather than do a routing lookup and send the ICMP message back to the person directly, it forwards that ICMP all the way to the end of the LSP that it was inside, and then it forwards it back. And so that can result in a really weird looking trace route. So you might see if you allow TTL decrement, so you might have 10 different router hops, and you might wonder, why are they all 80 milliseconds? Why is this one in Ashburn 80 milliseconds, and then this router in Chicago is 80 milliseconds, and then this one in San Jose is 80 milliseconds? That's because of ICMP tunneling. The ICMP message is going all the way to the end of that San Jose router before it comes back to you. So be aware of that if you see that pattern in Traceroute. That's an end result that can happen when you do this. There's another feature called link coloring. So again, it's called affinities or admin groups, depending on which vendor you're talking about. And it lets you do some additional constraints besides just available bandwidth. A lot of times these tend to be things like political. So for example, there are very large government customers who don't want their traffic to ever be routed through certain countries. So that's not a bandwidth thing, that's not a network thing, but that's something you need to implement. You need to say, these set of countries can never have these LSPs routed through them. So you can do that with link coloring. It basically gives you 32 unique color markings, and you decide what this color means inside your network and what you want to do with it. And then that gets advertised as a link attribute and it's flooded out in the bandwidth information. So again, geographic political boundaries, if you prefer to do the routing a certain way. You can also use it for maintenance activities. You can use it to move all LSPs immediately off of certain paths or certain types of devices. You can do some things like, for example, don't allow your core-to-core LSPs to go through your metro network, which it might find as available bandwidth. So any type of constraint that lies outside of bandwidth, you can use this for. And then there's a few downsides of using MPLS, and it wouldn't be right if I didn't talk about them. So remember, no protocol is perfect. One major drawback of MPLS is that it hides the topology changes related to your IP network when multiple exits exist. So say, for example, say you peer with a major network in San Jose and Los Angeles. So it's an Asian network, you peer with them in 2 locations in the US. These are your 2 exit points. And so your normal best path from Chicago would be to go directly to San Jose. But because of a capacity issue, that Chicago to San Jose path is full. And so MPLS decides you need to move this via Los Angeles. So you have to go all the way down to Dallas, over to Los Angeles, and then up to San Jose. The traffic doesn't know, hey, I've actually got a local exit in Los Angeles. I could use that. It's making that determination based on the IGP cost that occurred in Chicago. So Chicago thought San Jose was the best exit, and it used it. So even though you went through a router that could have been used as an exit, you didn't have that choice. And sometimes that's a good thing. That might prevent traffic changes, or that might prevent that external peer from filling up. And sometimes it's a bad thing. So it's something to be aware of. So here's the example that I was talking about in graphical format. Your purple LSP here is actually not using the exit in Los Angeles that it could. It's going all the way up to San Francisco, San Jose. Another big drawback is that the LSPs don't create themselves. So, unlike a lot of other protocols, there's no protocol that does all of the, like there's a protocol that does signaling, but there's no protocol that does the LSP creation. So it's ultimately up to the end user to figure out what LSPs they need, where they need them, and to go create and configure them. And so that turns out to be a pain. If you've got a complex network and you want a full mesh, that might be building thousands, tens of thousands of LSPs. So there's a bunch of different commercial software vendors out there that'll supply solutions. People like Wandel and Keratin. I think some of these guys have been bought. But there's some vendors that offer some very basic auto mesh capabilities too. So for example, Cisco IOS, you can pass it a list of all the routers in your network via like an access list, and it will go create an auto mesh to those networks. The downside is that leaves you very little control over your network. So for example, you need to remove a node from that mesh. Well, it turns out you need to actually remove the entire ACL. So it's not a very scalable system. Juniper doesn't offer anything like this at all. They say, if you have commit scripts and op scripts, go use that. So essentially, it's up to the operator to find a solution for go creating all these LSPs. The next interesting challenge is that LSPs act as an atomic unit. You can't take one LSP and send it via 3 different paths. The LSP has to go down one path. And so if you have very large LSPs relative to the size of the circuits, you get a packing problem. So say, for example, you have 3 different 6 gig LSPs, and you want to send them over 2 different 10 gig links. You'd only be able to fit 2 out of the 3. And so your 2 circuits route, and your other one could fit, but it doesn't know how to do that. And so that's an example where you might need to go create additional LSPs, not because you need more routers in the network or because you need a full mesh, but just to load balance. So if you go create a second parallel LSP, it can share the traffic across both of them. But again, that ties back into that original problem of the operator is now responsible for LSP creation and LSP monitoring. Another example is if you have mixed speed networks. So if you have high speed and low speed portions of your network, if you have a 3 gig LSP, you'll never be able to use an OC48 circuit. It'll sit there and do nothing because 2.5 gigs can't take a 3 gig LSP. So like I said, the workaround I talked about was manually creating LSPs. And then there's a lot of talk going on right now in standardization bodies about the ability to do forking of an LSP. So for example, the router knows that when this LSP gets above a certain size, it goes and creates dynamic numbers of smaller LSPs. And I don't believe there's any actual working vendor implementations of this currently, but I know there's a lot of vendors looking at it. Or there weren't the last time I looked into this. So that might be something to look at in the future if you have large volumes of traffic relative to the number of LSPs out there. And then there's also a bunch of gotchas when it comes to auto bandwidth. So it turns out that auto bandwidth isn't perfect. One classic example is when you have auto bandwidth running over unsubscribed links. So auto bandwidth, again, it's a very simple algorithm. It looks at what we think the traffic is now, and it does some basic calculations and says this is what we think the bandwidth should be going forward. But it doesn't know things like, hey, we're actually seeing packet loss on this link because it's congested. So here's an example. Say that you manage to oversubscribe a link, RSVP fills it up, and you get packet drops. All those packet drops cause TCP to throttle back, and the IP traffic rate goes down. And then auto bandwidth says, hey, the traffic went down. I can adapt to this, and I can continue to deliver it. So it'll sit there and continue to forward traffic via a congested interface because it doesn't know that there's loss out there. There's a couple new things on the horizon for being able to do kind of offline additional input into that, but I don't think there's anyone running. No one that I've talked to is running these in production. and it's probably not the kind of thing that you want to get into as a newbie to MPLS. Another thing to be careful of, there's a lot of routers that don't see layer 2 overhead. So for example, this is a big problem with Junipers. Any of the Juniper MT, MX series boxes, when you forward that 28-byte UDP packet and it consumes 84 bytes on the wire, the router doesn't see that. And it has to do with the original architecture of the M series, where the PIC stripped all the layer 2 headers before it ever made it to something that could count. And that's not the case today, but they've never actually fixed it in software. So you can very easily have a small packet size DDoS that's completely filling your link, and auto bandwidth says, oh, it's only doing 7 gigs, I think everything's fine. So that's something you have to watch out for. You have to build in levels of overhead for little small amounts of dynamic changes, and then you just have to monitor your network, and if you see loss out there, you need to go react to it in some way. And that's it. Questions? Anybody? Bill?
Can you say a few words about the size of the configuration files necessary for an MPLS network of a particular scale? For example, if you had a 30 or 40 node network, how many lines of configuration are required to do the sort of things that you're talking about here? And the other question has to do with the debugging of these things. I understand that at every MPLS switch or router, whatever you want to call it, there's going to be label switching that happens. So I'm kind of curious about the debugging of problems when they come up, when you may need to sign on to each router to take a look at those labels. Is that a practical issue?
So the size of the config files, yeah, you can very easily get some very large config files here. And there's a bunch of different ways that you can work around this. In iOS XR and Juniper, you can do things like groups. So you can take the standardized portion of the config, the things that you're going to apply to your 15 lines that you're going to apply to every LSP, and you can just have it done automatically to every new LSP. There's a lot of tools. So for example, Juno's commit scripts that we use, and op scripts to go create the LSPs themselves and to do all the dynamic expansion. But yeah, at some point you're going to have still a very large portion of the config, and it's your job to go manage all this. So you as the network operator need to be aware, oh, this LSP just got large, I now need to go add a new one. So someone has to monitor it, someone has to go log into the router and configure it, or someone has to write the tools to manage all this. And that's probably one of the biggest challenges of working with MPLS, is there's very few things to do that. And so it's usually up to each individual network operator to kind of figure it out on their own. And certainly at scale, it becomes really tricky. In terms of troubleshooting, it's not something that you really run into on a regular basis. You know, everyone has their bugs, and sometimes you need to go dig deep into what is this label and where is it going and why is it going there. But usually the troubleshooting that you see is, it's been a while since I've seen a significant one of those issues. Usually the troubleshooting that you see is more along the lines of, for example, why is this LSP routing the way that it's routing? You might have a path from Miami to New York that's decided that it needs to go through San Jose, and that's bad. So you need to monitor for that, figure out why, and it might be something as simple as you know, that LSP is coming out so large that it can't fit via the path that it wants to fit. Or we've seen instances where there's been software bugs. We've seen auto bandwidth decide that this LSP we think is doing 70 terabits, which is, that one's actually not so bad because it tries to reserve 70 terabits and usually doesn't actually get it. But it's more of a problem when it says, it's actually 200 gigs and it's a high priority gold LSP, and that it can find, and it'll find that by kicking off a bunch of other customers. So there's always bugs to watch out for, but it's not typical in my experience that there's things you need to go log into every router along the way and start troubleshooting MPLS operations itself. Phil?
Phil Rosenthal from IS Prime. Sorry. So two questions. So one is, Like you said, there isn't any feedback between MPLS and BGP, and would it perhaps be something that might make sense to implement in a protocol that when your LSPs start taking a longer path, that it could signal, hey, the metrics should increase? And the second question. So obviously, most people do not have the luxury of running, their own nationwide dark fiber network plus, their own IP network. But there are some networks that do, and if you are in that position, does it maybe get to the point that while the multi-services features might be useful to you, that some of the other like auto bandwidth, et cetera, might actually just be easier solved by just setting up more waves around the network if you own it?
So I'll do the last one first. That's always the trade-off, is sometimes it's easier to just throw more bandwidth at the problem, and sometimes you have to say, that bandwidth costs me a lot, maybe I need to solve it some other way. So the downside there, you look at your typical network who happens to own all this dark fiber, and they're dumping millions, tens, hundreds of millions of dollars into CapEx every year for better wave gear, more dense wave gear, cheaper wave gear. But there's real costs associated with that, even if you happen to be a $10 billion company who already filed bankruptcy 3 times and has the fiber and doesn't have to pay for that. There's still significant cost to adding that capacity. And so if you look at the typical architecture of a network, say the way that they transport stuff between New York and Ashburn, for example. That's a major corridor with a lot of traffic. And if you own that dark fiber and you light it with all of your own gear and you have terabits of capacity on it, but now that fiber's cut, you need to plan for, well, okay, my next best bypass path is to take it to Chicago and to take it over. And you have to put in all of that additional capacity. So you don't always need to micro-optimize everything with MPLS, but it gives you the flexibility to decide, well, putting in all of this extra capacity right now would be hugely expensive, or I can use this to better manage multiple diverse paths. So the question about the interaction of BGP, that's actually one of the more interesting things about MPLS is when you use MPLS to do traffic engineering, you're really only talking about how the traffic moves in your network, not where it's going. So the things that MPLS is very good at is handling failed links or failed routers, finding additional bandwidth in your network and using it. But it really doesn't react well to changes at the IP level. So in this example with the 2 peers, one in San Francisco and Los Angeles, if you lose that peer in San Francisco, it goes down, and so now all of that traffic needs to go to Los Angeles, or maybe even the guy in Chicago says, instead of doing that, I'm going to send it to a different peer somewhere else. MPLS reacts very badly to that. That's one where you're waiting a full cycle, a full adjust interval cycle, because now the traffic is not the LSPs themselves that have moved, it's the traffic has moved to a different LSP. And that's where you're waiting for that adjust interval, you're reacting to it, you're re-optimizing the network. There was a nanog presentation that Tom Scholl and I did a few nanogs back. You can go find it in the archives, where there was a theory proposed about taking this type of an architecture and extending it all the way out to the layer 3 edge. So for example, you might be able to do a kind of a reservation system looking at your egress capacity. So you might say, if I have a capacity to this pier in San Francisco and capacity in Los Angeles, I'm reserving, I'm actually letting RSVP know that the exit that it wants, the final destination, only has 5 gigs of remaining bandwidth available to this pier. And so I might want to then change my BGP best path algorithm. But that's not something that anyone was ever seriously interested in doing, so it kind of never went anywhere.
So I guess the answer is it would be nice if it were implemented, but nobody is actually talking about doing it.
It absolutely would be, and no one that I know of is, and if anyone is aware, please let me know.
Thanks.
Ralph Mullen, Internet Archive. So as far as I know, there's still no in-kernel implementation in a Linux kernel of MPLS, but there is a SourceForge package for it. Do you know if that is feature complete and like good enough to build a test network?
I don't. I'm a FreeBSD guy. So I'm sure there's probably some Linux people in here who can answer that question, but it wouldn't be me.
Jeff Nissen, Unite Private Networks. Could you comment on MPLS TP and maybe how that is distinguished from MPLS transport engineering? And then where it might apply in the network, application.
So that's not one that I've actually spent a lot of time dealing with, but MPLS TP, so when you look at how you build a transport networks, for example, there's a lot of vendors who are not Cisco and Juniper who want to get into the MPLS world and want to offer something different than the layer 2 solutions that they've been doing. And they were looking for kind of a simplified version of MPLS specific to doing transport. I really don't know enough about the details of MPLS TP just because I happen to have the luxury of working on a network with a full MPLS deployment. So it's not something that I ever got into, but there's a lot of people that are interested in it. Anybody else? Well, thank you very much.